You'll have a moment to jump back on this. I just want to show you the spurs today. We're going to take about 20 minutes of notes, maybe less, but it's all based on heat curves and phase diagrams, which are things that you're fairly familiar with. So I'm going to ask you to draw some structures or draw some pictures so you can kind of annotate what all those diagrams are supposed to entail. But then we'll jump into our lab and hope to conclude our lab in class. Priorities. Get this thing done. Are we struggling on drawing anything right now? What's iso in like geometry? The same. So isopropyl alcohol, right? How many carbons do you have? Prop means 3. So you have 3 carbons, so we're not putting alcohol group. No. It's isopropyl. It's not. It doesn't say like 2, or it doesn't indicate there's 2 alcohol groups. So how can I make this symmetrical, like the same with the middle carbon, right? So basically, I don't have one propanol because I don't have one with alcohol group on the end. I have one with alcohol group in the middle. So it's technically you could call it 2 propanol, and that would indicate to you that the alcohol group's on the second carbon. Another one? All right, put your lab away for the moment. You'll come right back to that shortly. I'm going to try to put a timer on myself. I'm going to yapper up here. That's 16 minutes. Let's see where we are. Okay, so essentially this is a quick review of some honors chem that we're kind of getting our explanations to the AP Chem level. So we're not just saying stuff, we're saying like meaningful terms that says a lot in a little bit because we have to be brief on our pre-responses. So quick, what types of compounds will evaporate most quickly? Those with what? Weak IMFs, things like what? Okay, who has London dispersion? Okay, everything is London dispersion, right? Just making sure literally everything is going to experience London dispersion, but who has the most prominent force being London dispersion? Okay, atomic solids. I was looking for just in general like non-polar, right? Non-polar molecules experience London dispersion, which would be the most quickly to evaporate. All right, so relate each of these properties for me. If you have a strong IMF, what does that mean for your volatility? It's hot. It's a hot. So what's volatility mean? No. You're thinking viscosity. Volatility. It means to evaporate. It's going to make a gas, right? So if you have a strong IMF, what does that do to your volatility? Lowers the volatility. It means you don't make a lot of vapors. You don't make a lot of gas in a readily available fashion. So what should that do to your vapor pressure? Should what? You gotta be like, enunciate words, people. Decrease, thank you. So if you don't make any vapors, you're not gonna have any vapor pressure because you're not gonna have any collisions with your container wall. And what should that do, the strong IMF, do to your viscosity? Increase it. What should it do to the surface area? Increase. What should it do to boiling point? Increase. Okay. So you know your relationships. Good. So within particulate diagrams, they like us to be able to indicate what's happening and identify if it's chemical or physical change. So which picture accurately portrays what's occurring when a liquid becomes a gas? Take a second to look at 1, 2, and 3. Liquid to a gas. And just hold up the number right when you're trusting me ready. Just you and me. Alright, you got 3 seconds. Alright, most of us are saying 3. Very good. So in terms of 1, what is this indicating? Atomic rearrangements, like really pulling everything apart, breaking bonds. So that's definitely a chemical change, not a physical process. You're going from liquid to gas. You're going from kind of a condensed state of matter to a non-condensed state of matter. So you essentially do overcome all of the IMFs. So is that, how is that indicated between 2 and 3? So this could almost look like solid because you're showing some IMFs between them all, and then you're showing just a couple here and there. So it still could yield like a condensed state of matter. So this might even be liquid, but this is the best answer because you're showing all of them being overcome. Notice that word is overcome. So that's what we want to try to say to indicate that we have taken particles and removed them from each other in a certain distance. Okay, what's this? What's this curve called? It's this guy. Maxwell-Boltzmann curves, good. What should, in terms of Maxwell-Boltzmann curves, they really related to gas particles and like their speeds in which they were moving. What impacted the speed of a gas particle? Kinetic energy, which we know we can alter kinetic energy by changing the temperature. So these are temperatures up here, negative 120 and 600 Kelvin. Just call this Kelvin. So indicate what's happening between the, CJ, this one's red, this one's green, this one's blue. Indicate what's the difference here, okay? Talk to your groups first, what you see. Talk about changing on colors. All right, come back to me. 3, 2, 1. Margaret's table. Can you tell me what's going on with this red one?
Well, there's a low temperature.
Okay. Yeah, 3 people. Yeah, come on.
Well, I know the areas under all of them are the same.
Okay, if this is the same sample of gas, yes, the area under each of these curves are the same. Very good.
And it's the lowest.
We can say velocity, but we're going to kind of say like molecular speed, right? So this is the average, right, versus this one versus this one. So this one's going to have the lowest speed, and that's due to the what? So everybody's saying low temperature, right? So low temperature indicates lower kinetic energy, which indicates slower moving particles, because kinetic energy is the measure of your energy of motion. All right, so Drew's table, tell me about the blue one. Highest kinetic energy, because it's at the 600, okay? And great, so the meters per second is sitting at 650 meters per second, so it's going to have the greatest speed, and that's because of the increase in temperature. So this is just a quick reminder, we're relating temperature and kinetic energy, and within that, we should be able to think about how this can relate to vapor pressure. Which of these particles, the ones at negative 120 or 600, should yield the greatest vapor pressure? Assuming all of these are gases. Which one? 600, why? Well, that's not the reason, though. Give me more about vapor pressure. Give me one for Christian. Yeah.
It has most kinetic energy, and it's going to cause the most collisions.
Okay. So I want to kind of mention that in 2 ways, okay? So increased kinetic energy does what to your collisions? Increases the number of collisions, which collisions on the container wall is what's going to cause the pressure. What else does it do? Somebody at your table? Not only does it increase the frequency, I'll modify this, not only does it increase the frequency, the what? The energy of force, the force of collision, let's say that. So it increases 2 things. Increases the frequency of collision and the force of collision, therefore it's going to cause pressure not only by nature of number of hits, but also the force of those collisions. Somebody had a question over here, Margaret?
Oh.
Good, yeah.
What's the y-axis?
Number of particles. I was going to hurry down a second ago, thanks. Okay, I think that's all I want to tell you here. Yeah, okay, so in terms of just relating one more thing to IMFs, which of these is going to have the weakest IMFs? Okay, they're all the same structure, right? They're all the same particle. They're all the same. So if they're all the same temperature, they would have the same molecular interactions. But the faster moving ones are definitely going to have the weakest attraction to each other, which is another reason you can also mention vapor pressure to be highest, because it's simply able to escape and it's not going to be held down by a partner attracting it. So that's kind of the relationship we want to make between kinetic energies, IMFs, and vapor pressure. So just take a minute and read what you need, and then we're going to move on. Because I'm going to draw a picture with this one. So basically, if you have evaporation occurring, where is it occurring within the system here? I'm going to make this in like a little glass. So this is a closed system. Where is the evaporation occurring? At the surface. Nothing's happening down here. This is all liquid, 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 liquid. Nothing's going to evaporate within. It's going to only be occurring at the surface. If we were boiling something, we can boil from beneath, by putting like fire underneath, and it would boil throughout. But evaporation occurs at the surface. And then condensation, again, because there's a cycle to this, will occur at the surface. So when are we're looking at, like, we know what kind of vapor or what kind of substances, what are the forces that interacting, but really we're looking also to see who's got the most kinetic energy. And if all of these are at 100 degrees Celsius and this is water, just the ones at the surface are going to be the ones that are actively evaporating. The ones in the middle are going to work their way up, but the surface ones are what we're looking for. So that's how we also relate this back to surface tension, because if you have weak surface tension, you have a lot of surface particles that have the kinetic energy to escape. Okay? Okay. So just a couple review pieces here. Now, sketch this big. Okay, so sketch this curve, and then we're going to kind of just annotate each piece so we can relate this to kinetic energy, IMF, and potential energy. So take out the whole paper, or half the paper. And some of you guys like to take your paper. I got you. No. So x-axis is time, y-axis is temperature in Celsius. Notice that was heat discovered chemistry. Remember, again, we are using Celsius a lot as opposed to Kelvin. You can pull your reference in the back of one of the papers that's provided to you. Yeah, I'll scroll down. You're good. So we're going to do this for water just because we know naturally a pretty good amount about water, boiling points and so forth. So to make it a little easier for taking notes on a graph, you'll notice that I put 1, 2, 3, 4, 5 on each segment, just so you can annotate and just say, like, segment 1, what's actually happening, segment 2, what's happening, and so forth. Notice the temperatures, the key temperatures are 100 and 0. It's really all I would really label in terms of what's on the y-axis. All right, my little Picassos, we're moving on. Okay, so in terms of part 1, see if you guys can give me some key phrases, key actions that are occurring in part 1. Talk in your group first for a second. All right, and come back to me. Marcus's table, give me some key points here. Quick and snappy. Okay, so temperature change is a big piece. So we've got ice, right? So I'm just gonna draw these like little balls, okay? So they're really close together, right? This is a solid. The solid itself has the potential to move, but we have to give it some, it's got potential energy inherently and also kinetic energy inherently. As you're increasing the temperature, we do have temperature change, right? So we could technically calculate the energy needed to cause that temperature change. Remember, energy and temperature, are they the same thing? No, so temperature is described in what unit? Temperature is described in what unit? Celsius, right? We have an axis here that indicates that. And then energy is described in joules. So what's the relationship between temperature and joules here? Q equals MCAT, right? So we could technically calculate this for water, knowing the mass, the specific heat of water, or ice, which we do know, and then the delta T. So we could figure out the quantity of heat added to cause this this change. So is this ice phase changing? No, okay, it's just simply heating up. So as it heats up, these particles, they get more active. So these little quote things are making them move a little bit more. They're just moving a little bit more. They're moving a little bit more. They're moving a little bit more. What's holding this solid ice together? Say again? Hydrogen bonds are the IMF. That's holding them together. Currently, the hydrogen bonds are pretty strong because they're relatively close, so the distance is small, Coulombic attraction is high. Okay, so that's what's happening so far. So as they start to increase their kinetic energy, because remember temperature and kinetic energy are essentially one and the same, they're going to start to move apart a little bit, but not enough to cause a phase change, but they're starting to heat up, they're starting to move a little faster. Then all of a sudden, boom, we hit this right here. What's it going to do there? So we hit melting point. I'm going to maybe say that a little bit better. Meet like 0 degrees Celsius, which is the melting point. Okay, so what starts to happen? Talk first, and then we'll chat. So basically talk about what's happening in part 2. All right, William Stable, help me out here.
So because it's the melting point, the IMFs are moving.
Okay, so I'm going to say IMFs are being overcome.
Oh, yes, overcome.
Okay. More? Okay, so it's starting to go from solid to liquid due to this overcoming of the IMF. So the hydrogen bonds are still present, it's just they're moving farther apart, so they're weakening. So I like the word weakening too. We're not saying breaking at all, because breaks, a bad word for this, that would be indicating bonds, not IMFs. What else is relevant here? Think way back. We're on this part. What is this part called? HF. Delta HF is called heat of fusion, which this is the energy required to melt water. What equation plays into this? Q is equal to moles times delta H of fusion. For water, delta H of fusion is 6.01 kilojoules per mole. Okay, it's good review so far. Oh, what's happening with the kinetic energy with this plateau? Okay, so there's no change in kinetic energy because what's not changing? If temperature is not changing, we can't have kinetic energy changing, right? But these things are definitely moving. Energy is changing. What energy is changing? Potential energy. As they're moving farther apart, they have a change in their potential energy or during this entire process of phase change. So this is a phase change, and potential energy does change. Okay, part 3. Go ahead and see if you guys can knock out 3 and 4, thinking about what's happening, trying to use the right words. Oh no, what did I do?
still under the IMF there. So yeah, they're weaker.
Go and do 5 if you're done with 4. All right, let's recap 3 and 4 real quick. All right, so temperature changes, therefore kinetic energy changes. And I just want to give you some more of those verbs that you learned about in the first video. Remember we talked about rotational, translational, vibrational energy, or movement. You do remember this? End of the first video. Okay, thank you. So that's just another way you could describe that, but without saying overcoming IMFs. And then secondly, in 4, which is the next plateau, that's when we're vaporizing. That's when we'll include delta H vaporization. Do note there was a difference in the graph, and there's a much bigger difference between the delta H bath and delta H fusion. So this is delta H fusion, right? And this is delta H vaporization. Which is bigger? Delta H bath, right? Why would this one have to be so much larger? Which you can see from my numbers here. The first one's like 6.01 or something kilojoules per mole. This is 40.7. Right, so when you're melting, you're just kind of moving them a little bit apart. You're kind of overcoming, let's say, half the hydrogen bonds or something like that. It doesn't take so much energy to do that. But if you're totally wiping out all IMFs to allow the gaseous phase to form, you do have to put a lot more energy into that process. Therefore, delta H vaporization is much higher. Okay, so sometimes they'll have you do a comparison there. And then again, potential energy is changing on the plateaus, kinetic energy is not. And then lastly, we're at gas. They speed up. I mean, they heat up. Kinetic energy changes. Yeah, okay. All right, so I'm gonna show you one more thing with a phase diagram and then I'll stop for today, okay? So give me a thumbs up when you're good. Okay, so that's a good review, and this definitely relates to the condensed states of matter, which we're referencing right now. I'll put this up if I need to later. Ooh, ah. Yeah, that's what we just did. We just went through all of that. It's great. Okay, so draw a phase diagram. If you can't see this very well, I'll sketch one on the board. I just want to indicate some key parts here. This was in your reading, so I don't feel like this is definitely new information at all. But a phase diagram is going to give you information about a single substance. So there's one phase diagram for every substance in the world, be it elemental or compound. And the x-axis is what? Temperature, usually in Celsius, it can be in Kelvin. And then the y-axis is pressure. It can be a torr in atmospheres, kilopascals, whatever pressure unit is wanted at that for this particular graph. And on the phase diagram, it shows you the phases that will occur at each combination of temperature and pressure that we can make. So with those combinations, we'll have solids, liquids, and gases. So solid is always your upper left-hand side, liquids the next, and then gas is the farthest to the right, kind of. And it does vary. So I drew one where I started up higher. This depends on how you label your graph. You can see this is water. I think this is water. and then this right here is for carbon dioxide. So they will look different. Their graphs will have different slopes. They'll have different points because everything has a different boiling point, melting point, critical point, sublimation point, etc. at different pressures. So to interpret this appropriately, you need to know a couple words. If I say normal means what pressure? 1 atmosphere. So if we're generally, like we live around sea level, so we're generally around 1 atmosphere. What would be our, right? So this is 1 atmosphere here. What would be our melting point for water? Melting point for water? Sorry, I heard some hundreds. 0 degrees Celsius, right? So all you're doing is looking at the intersection between pressure of 100 and then the point at which you transition from solid to liquid, that would be considered melting, and then drop that line down, and that's your literal melting point. That's the temperature at which you melt. And then as you transition to boiling, you're going from liquid to gas. So the intersection between 1.00 atmospheres and this on the line separating liquid and gas, that would be your boiling point. So if I was on Mount McKinley, Mount Everest, any mountain, okay, what's happened to our pressure? It's decreased, right? So if you don't remember this, I think we even drilled the mountain, and we were here, and then we were here. Maybe this is some other stone. Okay, so we have pressure pushing down on us a lot when we're at lower elevations, and just a little bit of atmospheric pressure pressing on us when we're at higher elevations. That's why the pressure is lower, air pressure is lower. So if we're at a lower pressure, we're not going to have as much pressure pushing down on the substance, so it's going to be able to vaporize easier, overcome us easier. All the points will be technically lower. So if you have here, whatever this pressure is, you can definitely still make the same connection between, okay, for water you can't. So at this pressure, what's the only thing this substance is able to do? Right, the connections between solid and gas, so it can only sublime. So you would see things just going straight from solid to their gaseous phase, not any liquid would form. Unless you increase the pressure more, you could then go up to, where would this be? Like 218 atmospheres. Bottom of the ocean, you could definitely have a high end, or actually a lower melting point, because it would be over here, and you could have a higher boiling point, because that would be over here. So the slope of this line is definitely very important because it will cause some skewing of, is the temperature going to lower or increase for whatever phase change is occurring. I'll go over critical point at the end of lab, okay? So let's pull back out the lab, and I'm going to tell you what we're going to do just for time's sake. Okay, so I'm going to assign you guys groups. Okay, we're in 7 groups. I might have to move. I got 3 and 4 people, so I need to just make sure I got enough people wherever. But essentially, you guys are each going to be assigned one of these to be that's your variable you're testing. And with this, you're getting your temperature probe. You have to use Logger Pro to graph it. But essentially, we're looking for what data? We're looking for what? What data are we collecting in this lab? The delta T, where we're looking at initial temperature and then final temperature. That lab tells you specifically how to achieve that. If you need some help, let me know. But I'm going to assign you guys one of these. And as your group has now been assigned that chemical, you're going to run 2 trials on it so we can get some valid data. Because it might take a second to kind of figure out how you're going to set it up and read the data points so you get valid data. So running 2 trials won't take you very long. And try to keep some constants here. So like you're going to get a little square of filter paper. Try to use the same size squares for each trial. Try to use the same amount of liquid for each trial. Try to make sure you're putting the same place for each trial, and so forth. After this, we'll bring our data back to the front. You guys will fill out this data table, of course, with our additions, like acetic acid and so forth, so we can look at the temperature differences. And then as a class, we're going to try to conclude and relate this back to IMS. Okay? So let's see who's going to get what. Acetic acid, acetone, methanol, iso, ethanol, butanol, hexane. But my 2 groups, I have a big group here. So one of you guys come up here, because I don't think we're in 3s and 4s. Yes. So for the last two, those have to be done with the fume hood. I'm not going to turn the fume hood on. It's just we don't want to inhale those. Literally, we don't want to inhale any of these, but we don't specifically want to inhale those because one butanol smells horrible, and hexane is just not good for the soul. So I'm going to keep you guys towards the back so that you guys can use the fume hood. Okay? Go to your groups. And I'll say goggles, goggles, goggles. I need the hexane and the butanol here. If you're not numbers, don't be here. If you're at a lab station with a desktop, turn the desktop on. I'll be right there to get Logger Pro pulled up for you. If you're not at a lab station with a desktop, you get a cool Logger Pro necklace. You should feel cool now. Everybody needs my corner tables, I need some go links. You guys know the process here. Alright, these are the little filter papers and these are the rubber bands. Get set up first and then you'll come for your substances. I just have to throw them in Please read the instructions in the lab. You guys can read, you're big boys and girls. You got this. Believe in you. A couple of you guys are going to figure it out. Did somebody take the isopropyl alcohol?
Smaller than yours.
Alright, listen up for me, okay? Ready? What I've done for you is I've provided the samples, the first 500 samples here, because all you're going to do is bring your probe, somewhere on your computer, probe, and you're gonna, or actually, since I've only got 1, 3, 2, yeah, that works. It is in order, 1, 2, 3, 4, 5, so don't mix them up. The methodology I'm keeping careful number because it's very volatile, so I'm keeping careful number. So you can bring this to your station, dip your probe in it, and then get your initial temperature, and then get your final temperature. It would be great if you could graph it because you can see the dip or the increase of, I don't want to spoil it for you, but you'll see the change in temperature. So if you can get the graph to work for you, you can set the axes from 5 over to 35. If not, you can just graph it, and you just have to understand the dip to find the initial and the final. As it is right now, it's about, what, 25 degrees in the room. That is not your initial temperature. You're going to get your initial temperature once it's saturated, your filter or saturated with your substance. Hence what we're doing 2 trials. If you're going to do 3 trials, $5 are 3 trials, okay? So if you want to have your test your rack out, it might be easier for you to have them at your station. I'll ask you for 2. that's how you're taking down your probe off the side of the table. Please follow the instructions. You guys will have enough time for in my room.
What is a good 10 centimeter?
Literally like, you know what centimeters? It's literally like this, like that. You want to pick a centimeter? You want 10 centimeters. Well, 3.54 somehow is 1 inch. So it's down to this, right?
You're on the very lot. Don't look at me like that, teacher.
I was following you.
3.
Why would you?
Hey, you guys want another one? I think that's 14. Wait, no, I don't have it.
Oh, that's not funny how that worked out.
Like a register that like I was kind of God, my thumb is gonna fall off and Gigi's not gonna do anything about it. I watched that.
If everybody can get their second trial done in the next 2 minutes, that would be phenomenal. Yeah? You just need to go to data collection at the top. But regardless, you still have the data. You can still see the data. You can still see the temperature dropping in the red number. You can definitely collect your own that way. No, the time, if you want to make it work right, then go to data collection and modify the time collection. Yeah.
So like ours had stopped measuring at 270, but now start going back up again.
Okay, but you can see your temperature. Somebody needs to watch the temperature so that you
Yeah.
get the inflection point.
Okay.
Go watch it. Go. Christian.
You should be close to getting that second trial done. Thank you, Mom. Clean up your last station where you can. I'll see you back at the front very soon. The data should be here before.
Do you want his initial? Average for both.
So your overall bill for trial one, your overall bill for trial two, give me the average.
That's 20. It's 10. It's 20. Yeah, you have 20 divided by 2 is 10. That's not right to 0?
What's your?
We're 2. We're not acetic acid.
Oh my god. Well, this isn't
That's
order.
not in order. It's up for us. Asking on the chart? Oh, yeah.
Right. So what was your average? What was your temperature change on one?
9.4. And our second was 10.6.
Yours was the both. So give me some sleep, big girl.
Okay. Hold on.
All right, your samples should go back to the same location on the test tube rack so I know what they are. Put parafilm over them so they don't evaporate. Put all the materials back at the lab station. I'll see you here in 2.
That's gonna be our answer? What are you guys on? No, it should be not, it should be, that's like the change overall that was. Absolutely. All right, so you guys are going to write down the data, and we're going to modify this conclusion just a tad. Yeah. Send me somebody with data. Send me somebody with data.
Wait, 2 propanol to oxypropanol.
Yeah. Send me the back. I need some data. You have like 30 seconds.
11.5. Okay, 11.5.
Acetic acid, where are you at? Thank you. All right, and I am starting, that last group's going to give me some data. What's the delta T? 2.6? Okay. All right, so here, Enlo is modifying the conclusion and the analysis. You got to listen to me, okay? So you have already written down the data, yes? You're writing down the data. Ethanol, 11.85, 2-propanol, 11.1, 1-butanol, 2.6, acetic acid, 7.3, methanol, 17.7, hexane, 11.55, acetone, 10.0. So I want you to order them from the way that it looks according to this data, from the ones that have the strongest IMFs to the weakest IMFs. So this is, Emma's making it her own analysis. You ready? Okay, so 1, list from data, strongest IMF to weakest IMF. And you must maybe discuss that at your group so you know like what you're thinking out loud. Based on this data. I can scroll back up if I need to. Andrew, don't scroll, which way? So you got ethanol, acetone to left. Can you take this one? That was pentane. You see acetic acid. I was scratching it out in one. All right, so your 3 questions right now are, list from the data, like we are doing data-driven decisions, okay? So you must talk about why these delta T's occurred and what would indicate a strong intermolecular force versus weaker ones. So 1, you're listing data from strongest, using data, strongest IMF to weakest IMF. 2, theoretically, who should have collectively the strongest, or exhibit the strongest IMFs, and then who should exhibit the weakest IMFs. You'll compare 2 and 1, and then talk about why the theoretical data may or may not agree with the experimental data. Okay? Why might number 1 and 2 not agree? Target your groups. Well, it may be. So yeah, you know how to rank your IMFs. So yeah, molar mass might be your. Are you looking at hydrogen bonding? There's other ways to do it too, but that's a good way. What are you talking about breaking? Ranking. Yes, you're theoretically ranking them. I think you said breaking. I was like, no. Why can't I move this?
Yeah, it should be good for.
I just want to get a consensus on my fill in the blank question, so I know you're on the right track. This will give me confidence in you. The greatest delta T, so the greatest temperature change, is indicative of the what IMF? Why the weakest? So it takes less energy to overcome the IMFs between 2 weakly bound or weakly attractive molecules. So why would that give us the greatest temperature change? So evaporation is a what process? Endothermic. So we're going from wet to wet? Liquid to gas, which we know that's an endothermic process because it takes the energy to pull apart a liquid from a gas. So that's an endothermic physical process. And if you have a really weak force, you can do that over and over and over and over and over and over and over again very quickly, causing a very great, significant depression in temperature, which gives us a large temperature change. So this is going to be weakest force, and then you've ranked them, and then this is just a little background for you. Going from there, are you guys okay on 2? That means you have to go back and look at structures, consider IMFs, collective IMFs like LV and yeah, 2 propanol nicer.
Oh my gosh, it's so big.